Hello, my friend. Tonight, let's leave behind the noise of the day and drift gently into a quieter place. A place where space bends, time stretches, and gravity reveals its hidden poetry. As you settle in, I'll guide you through the mysteries of general relativity, not with equations or stress, but with calm stories of curved space and ripples in reality. So close your eyes, relax your thoughts, and let's float together into the fabric of the cosmos. Chapter 1. What is general relativity? When you look up at the night sky and see the moon slowly drifting across the heavens, or witness a shooting star tracing a quiet arc, you're observing the graceful ballet of celestial motion. For centuries, humanity tried to explain why things fall, why planets move, and why the universe feels ordered yet endlessly mysterious. For a long time, gravity was thought of as a force, an invisible pull between objects, growing stronger with mass and weaker with distance. Isaac Newton gave us this elegant idea, and it served remarkably well for over 200 years. It explained the fall of the apple, the tides, and the orbits of planets with unmatched precision. But there were things it couldn't fully explain. And at the dawn of the 20th century, a new way of thinking would quietly emerge, an idea that would change not just physics, but our very understanding of space, time, and reality. General relativity, developed by Albert Einstein and published in its complete form in 1915, is not merely a better version of Newtonian gravity. It is a complete transformation of how we understand the structure of the universe. It tells us that gravity is not a force at all. Instead, it is a manifestation of geometry, a warping of the very fabric of space and time caused by the presence of mass and energy. This shift in perspective is both subtle and profound. In Newtonian physics, space and time were fixed and absolute. They provided a rigid stage upon which objects moved and forces acted. Time ticked evenly for all observers, and space was flat, unchanging, and indifferent. The force of gravity, in this model, acted instantaneously across space, pulling masses toward one another without any physical medium through which that influence traveled. This worked well for celestial mechanics, but it left a deep conceptual gap. What exactly was transmitting this force, and why did it work so perfectly for some cases, but not all? For example, Newtonian gravity could not account for small anomalies in the orbit of Mercury. For decades, astronomers noticed that Mercury's orbit precessed slightly more than Newton's laws predicted. The discrepancy was small, but persistent. It became one of the many small puzzles that hinted something deeper was at play. Einstein's answer was to rethink gravity entirely. Instead of viewing it as a force, he proposed that mass and energy warp the geometry of spacetime itself, and that what we perceive as gravitational force is simply the result of moving through this curved geometry. To build this new theory, Einstein relied on a mathematical tool called Riemannian geometry, a branch of differential geometry capable of describing curved surfaces and higher dimensional spaces. With the help of mathematicians like Marcel Grossmann and David Hilbert, Einstein formulated a set of equations that related the curvature of spacetime to the distribution of mass and energy within it. These became known as the Einstein field equations. Although abstract in appearance, these equations serve as the core blueprint for describing everything from orbiting planets to the dynamics of expanding galaxies. The key insight that led Einstein to this realization came from a deceptively simple thought. He imagined a person in free fall, dropping inside a sealed elevator. Inside, that person would feel weightless, unable to tell whether they were falling on Earth or floating in deep space. This thought experiment became the foundation for what Einstein called the equivalence principle. The idea that locally, the effects of gravity are indistinguishable from those of acceleration. From this sprang the realization that gravity might not be a traditional force at all, but something more fundamental. a clue that geometry itself might govern the motion of objects. In general relativity, mass and energy tell spacetime how to curve, and curved spacetime tells objects how to move. It's not that planets are being pulled by the sun. Rather, the sun warps the geometry of spacetime around it, and the planets follow the natural paths, called geodesics, within that curved geometry. These paths may appear as ellipses or orbits, but they are simply the straightest possible lines in a curved environment. Much like how airplanes follow great circles across the globe, celestial bodies are following their own optimal paths, shaped not by a force, but by the terrain of spacetime itself. This concept may seem abstract, but its consequences are very real. Light itself, which always travels in straight lines in flat space, follows curved paths when it moves through curved spacetime. This leads to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around massive objects like galaxy clusters, forming arcs or even rings in the sky. In this way, spacetime acts like a cosmic magnifying glass. One of the earliest and most celebrated confirmations of general relativity came in 1919. British astronomer Arthur Eddington led an expedition to observe a total solar eclipse. During the brief darkness, stars near the sun's edge became visible. According to Einstein's theory, their light should appear displaced from their usual positions due to the curvature of spacetime around the sun. Eddington's measurements confirmed the prediction, and Einstein's name became synonymous with genius almost overnight. The Newtonian view of gravity had been challenged and surpassed, not by contradiction, but by deeper understanding. General relativity also provides insight into the passage of time. In regions of stronger gravity, near planets, stars, or black holes, time passes more slowly compared to regions of weaker gravity. This effect, called gravitational time dilation, has been confirmed experimentally in a number of ways. One involves placing highly precise atomic clocks at different altitudes. Clocks at higher elevations, where Earth's gravitational pull is weaker, tick slightly faster than those at sea level. This might sound like a minor curiosity, but it's crucial for technologies like GPS. Satellites orbiting Earth experience both weaker gravity and higher velocities, requiring time adjustments from both general and special relativity to provide accurate positioning data. Another prediction of general relativity is the existence of black holes, regions where spacetime becomes so curved that not even light can escape. These are no longer speculative objects. Observations of stars orbiting invisible companions, as well as gravitational wave signals from colliding black holes, have confirmed their reality. In 2019, humanity saw the first image of a black hole's shadow, captured by the Event Horizon Telescope, further validating Einstein's ideas at the extremes of physics. General relativity also gives us our best understanding of the universe at large. The equations, when applied to the universe as a whole, predict that spacetime itself can expand or contract. This led to the development of cosmological models that describe the Big Bang, the moment our universe began from a hot, dense state, and has since been expanding for over 13 billion years. The discovery of cosmic expansion by Edwin Hubble in the 1920s gave observational support to these models. Decades later, the observation of the cosmic microwave background radiation provided further evidence that the early universe was indeed hot and dense, just as the equations suggested. Interestingly, Einstein initially resisted the idea of an expanding universe. To maintain a static cosmos, he introduced an additional term into his equations called the cosmological constant, a kind of repulsive force to counteract gravity on large scales. When Hubble's data showed that the universe was expanding, Einstein reportedly called the cosmological constant his biggest blunder. Ironically, modern cosmology has resurrected the idea in a new form to explain dark energy, the mysterious phenomenon accelerating the expansion of the universe. Despite its remarkable successes, general relativity remains incomplete. When physicists attempt to apply its principles to extremely small scales, such as the interiors of black holes or the earliest moments of the universe, they encounter contradictions. The smooth, continuous nature of spacetime breaks down when quantum effects dominate. Reconciling general relativity with quantum mechanics is one of the most profound, unsolved problems in modern physics. It suggests that there may be a deeper theory still waiting to be discovered, one that includes both gravity and quantum principles in a unified framework. Still, general relativity stands as one of the most beautiful and successful theories ever conceived. It continues to pass every experimental test, and its predictions have transformed both our philosophical and practical understanding of reality. From the gentle tug of gravity on Earth to the majestic arcs of galaxies bending light across the cosmos, general relativity reveals a universe in motion, a universe not fixed in stone, but written in curves. To grasp general relativity is to understand that the universe is not just a collection of objects, but a living geometry. Every particle of matter, every flash of energy bends the structure of reality itself. We do not float in a static void. We ride the contours of space-time, shaped by the presence of stars and shadows of mass. Even the empty spaces between galaxies are not truly empty. They are woven with invisible curvature, stretched by the expansion of the cosmos, and marked by the gentle pull of gravitation that never quite lets go. And in this quiet realization, something stirs, that you, a single mind afloat in space and time, are also part of this vast geometry. You are not outside it, you are a ripple in it. Your heartbeat bends it, your presence shapes it, just as it shapes you. General relativity does not only describe what the universe is, it reminds us softly that we belong to it completely. Chapter 2. The Geometry of Spacetime. To speak of the universe without geometry is to describe a melody without pitch. Geometry is not simply a language of shapes and forms. It is the architecture of physical law itself. In general relativity, the geometry of spacetime is more than a backdrop. It is an active participant in the unfolding story of the cosmos. Where classical physics once treated space and time as rigid, unchanging, and absolute, general relativity replaces that notion with a richer, more fluid understanding. Space and time are merged into a single entity, spacetime, whose shape and curvature are dynamic, determined by the contents of the universe itself. The concept of space-time curvature is central to general relativity, but it cannot be grasped through everyday intuition. In our daily experience, space seems flat. Objects move in straight lines unless pushed or pulled, and distances appear consistent, no matter where we are. But these are local approximations. On cosmic scales, or in the presence of strong gravitational fields, space and time bend subtly, then severely. To understand how this happens, one must think not just in terms of motion or forces, but in terms of geometry itself changing from point to point. Curved spacetime is not simply a metaphor. It is a literal description of how the distances between points and the intervals between events vary due to mass and energy. Just as a sheet of paper can lie flat or be crumpled into complex shapes, the fabric of spacetime can be flat or curved. But unlike a sheet, spacetime does not curve into a higher dimensional space that we can observe directly. Its curvature is intrinsic, meaning it can be measured from within without referring to any external frame. This is where Riemannian geometry becomes essential. Developed in the 19th century by Bernhard Riemann, it provides the mathematical framework for understanding curved surfaces of any dimension. In general relativity, the geometry of spacetime is described using a specific kind of curved four-dimensional manifold, 3 dimensions of space and 1 of time. The curvature of this manifold is encoded in a mathematical object known as the metric tensor, which specifies how distances and times are measured locally at each point in spacetime. Unlike in Euclidean geometry, where the metric is fixed and simple, the spacetime metric in general relativity is dynamic and influenced by the distribution of mass and energy. If this sounds abstract, it's because it is, but it is also grounded in observable reality. The shape of spacetime affects everything that moves through it: planets, light beams, even time itself. The geodesics, the paths of least resistance, or the straightest possible paths through curved spacetime, are determined by the geometry described by the metric. In flat space, a geodesic is a straight line. On the surface of a sphere, it becomes a great circle. In spacetime, it is the trajectory a free-falling object follows, even if that path appears curved to an outside observer. What is profound about this framework is that objects in free fall are not being pushed or pulled. They are simply following the geometry laid out for them. When the Earth orbits the Sun, it is not being attracted in the Newtonian sense. Instead, it is following a geodesic in the curved spacetime created by the Sun's mass. If we could somehow eliminate the Sun while keeping Earth's velocity unchanged, Earth would no longer follow a curved path. It would shoot off in a straight line, according to the now flat geometry of empty spacetime. Different configurations of mass and energy generate different curvatures. A small planet creates a gentle well in spacetime. A massive star produces a much deeper one. A black hole represents a region where the curvature becomes so extreme that geodesics loop inward and no paths lead out. These curvatures are not imaginary or invisible. They have measurable consequences. Light from distant stars bends around massive objects, travel times for signals vary near dense bodies, and the structure of spacetime itself determines the large-scale shape and fate of the universe. It's also important to understand that spacetime curvature is not localized. It propagates. A sudden change in the arrangement of mass, such as two black holes merging, sends ripples through the fabric of spacetime. These ripples, known as gravitational waves, are tiny distortions that travel outward at the speed of light, carrying energy and information across the cosmos. Their detection, first achieved by LIGO in 2015, provided direct evidence not only of black holes, but of the dynamism of spacetime geometry itself. One of the elegant features of general relativity is that it eliminates the need for action at a distance. In Newtonian gravity, two objects can influence one another instantaneously across empty space. In general relativity, the influence of mass on spacetime geometry propagates at finite speed, no faster than light. This not only aligns gravity with special relativity's speed limit, but also creates a natural framework in which gravitational influence is embedded in spacetime's shape itself. The behavior of time within curved spacetime is another consequence of this geometry. In general relativity, time does not flow uniformly. The rate at which time passes depends on the gravitational potential, a measure of how deep within a curvature well an object lies. A clock closer to a massive body ticks more slowly than one farther away. This effect, called gravitational time dilation, is not merely theoretical. It has been confirmed with atomic clocks placed at different altitudes on Earth, in satellites, and even on airplanes. Time, as described by general relativity, is a coordinate that bends, stretches, and flows in ways utterly dependent on the geometry around it. Spacetime geometry also dictates the very structure of the universe on the largest scales. By applying Einstein's equations to the universe as a whole, cosmologists derive models that describe how the cosmos expands, curves, and evolves over time. These models predict that spacetime itself can have global curvature, flat, open, or closed, depending on the total energy density of the universe. Observational evidence from the cosmic microwave background suggests that our universe is very nearly flat, though not perfectly so. But even this apparent flatness is a local property of the observable universe. the full geometry of space-time may extend far beyond what we can see. On even larger scales, space-time geometry underpins the development of cosmological inflation, a rapid expansion of the universe in its earliest moments, which smoothed out irregularities and seeded the structures we observe today. The subtle geometry of space-time during inflation left its imprint on the cosmic microwave background, visible today as tiny fluctuations in temperature and density. These fingerprints of geometry continue to inform our understanding of the universe's origin and fate. One fascinating implication of space-time geometry is that it is affected not only by matter, but also by energy. This includes dark energy, a mysterious form of energy that permeates empty space and accelerates the universe's expansion. Dark energy contributes to the curvature of space-time not by attracting mass, but by creating a kind of repulsive effect on cosmic scales. The discovery of this accelerated expansion in the late 1990s revealed that geometry and energy are inextricably linked, not just locally, but across the entire cosmos. Despite its successes, the geometric description of gravity raises deep questions. For example, at the center of a black hole lies a singularity, a point where space-time curvature becomes infinite and the laws of general relativity break down. Near such extremes, the smooth geometry of space-time may no longer apply. Physicists suspect that a quantum theory of gravity, not yet discovered, will eventually replace the classical picture and reveal a more granular structure of space-time itself. Nevertheless, the geometric vision of general relativity remains unmatched in elegance and accuracy. It reduces gravity to nothing more than a change in the fabric of existence. There are no invisible forces, no instantaneous influences, only the bending and flexing of a living, breathing space-time. The orbits of planets, the bending of light, the passage of time, and the expansion of the universe all emerge naturally from this geometry. It is not simply the arena in which physics takes place. It is the thing that is physics, in one of its purest forms. And so as we drift through this invisible geometry, we are not merely passengers on a cosmic journey. We are part of the geometry itself. Each breath, each heartbeat, gently shifts the curvature of the world around us, even if we can't feel it. Every object in the universe contributes its presence to the shape of space-time, just as every fold in a sheet is influenced by every crease nearby. In that quiet thought, there is a kind of existential grace, that even in the absence of motion or noise, you are never truly still. You are always embedded, always woven into the fabric of something greater, part of the cosmic shape that holds stars, galaxies, and the soft ticking of time. Chapter 3. Time dilation and gravitational time travel. Time as we experience it seems universal. It ticks forward steadily, indifferent to our movements or our position in space. From our everyday perspective, time appears absolute, constant, and evenly paced for everyone. But this is an illusion born of limited perception. In truth, time is deeply relative. It flows differently depending on your speed, your location, and the gravity around you. Under the lens of general relativity, time reveals itself to be as dynamic and malleable as space itself. The result is a universe where time can stretch, compress, and even lead to forms of travel that defy our everyday intuition. The concept of time dilation emerges naturally from the structure of space-time in general relativity. It describes the way in which time passes at different rates for observers in different gravitational potentials or moving at different velocities. This is not simply a theoretical quirk. It is a rigorously tested and measurable effect. In regions where gravity is stronger, time ticks more slowly compared to regions where gravity is weaker. This means that a clock near a massive planet, a star, or a black hole will accumulate less time than one in deep space. This slowing of time is not due to mechanical interference. It is not a malfunction. It is a fundamental consequence of how space-time itself is shaped. To understand why this happens, one must look again at the relationship between mass and geometry. In general relativity, massive objects bend the space-time around them, and this curvature affects both space and time. When a clock is placed in a gravitational well, it measures proper time, the time experienced along a path through space-time that is curved more steeply near massive objects. To an external observer at a higher altitude, that same clock appears to tick more slowly. The deeper in a gravitational well an object lies, the more dramatically time stretches for an observer outside that well. This is not a phenomenon confined to extreme environments. Even on Earth, time dilation is measurable and must be accounted for in modern technology. Atomic clocks flown on aircraft or placed at the tops of mountains run slightly faster than those at sea level. The global positioning system is one of the most striking demonstrations of this principle. GPS satellites orbit Earth at an altitude where gravity is weaker than on the surface. As a result, their internal clocks tick faster, by about 45 microseconds per day, compared to clocks on Earth. If uncorrected, this would cause GPS calculations to drift by several kilometers each day, rendering the system useless. Engineers compensate for this relativistic effect, confirming not only the theory's accuracy, but also its practical necessity. Beyond the everyday implications, time dilation becomes more dramatic in extreme gravitational environments. Near a neutron star or a black hole, time can slow to a crawl compared to a distant observer. In theory, if someone hovered just above the event horizon of a black hole, avoiding being pulled in but remaining deep within the gravitational well, their time would pass incredibly slowly relative to someone far away. Hours for the distant observer might correspond to mere minutes or even seconds for the person near the event horizon. If that person were then rescued and brought back to normal space, they would emerge having aged far less than everyone else. In this sense, gravitational time dilation creates a form of one-way time travel. A traveler can move into the future more quickly than those left behind. This idea has entered the public imagination, especially through science fiction and films, but the underlying physics is very real. It does not require hypothetical machines or violations of physical law. It only requires access to extreme gravity and the ability to resist falling in. In practice, surviving such conditions is extraordinarily difficult, but the theory offers a tantalizing glimpse into what is possible. Time travel into the future is not only allowed by general relativity, it is unavoidable in certain scenarios. Another form of time dilation arises from motion itself. According to special relativity, which general relativity subsumes and extends, time also slows down for objects moving at high velocities. The faster an object moves, the slower its internal clock ticks compared to a stationary observer. This effect is called kinematic time dilation, and like its gravitational counterpart, it has been tested extensively. Experiments with high-speed particles and accelerators show that unstable particles moving near the speed of light decay more slowly than those at rest. Time for them stretches, and they live longer than expected, not because of any external interference, but because motion alters the passage of time. This too has real-world applications. The muons produced by cosmic rays in Earth's upper atmosphere decay rapidly and should not survive long enough to reach the ground. Yet they do, because their high speed causes their internal clocks to tick slowly, allowing them to travel farther before decaying. This observation matches perfectly with predictions made by the theory of relativity. These two types of time dilation, gravitational and kinematic, are often seen as distinct effects, but general relativity unifies them. Both result from differences in the geometry of space-time as experienced by different observers. Whether it's motion or gravity that creates the discrepancy, the underlying cause is the same: the space-time path each observer follows and the curvature along that path. When taken to extremes, time dilation raises deeply intriguing possibilities. If a civilization could orbit close to a black hole without crossing the event horizon, it could in principle witness immense stretches of cosmic time in what, to them, would feel like a brief moment. The future of the universe could unfold before their eyes, while they barely aged at all. This is not just fantasy, it is a direct consequence of the math. General relativity permits such trajectories through space-time, and nothing in physics forbids such one-way journeys into the future. Of course, returning from such a journey is more difficult. Gravitational time travel, unlike the fictional time machines of science fiction, cannot reverse itself. The equations of general relativity are time-symmetric, but the conditions necessary to travel backward in time remain elusive and possibly forbidden by deeper physical laws. Solutions to Einstein's equations do exist, like the Gödel metric or closed time-like curves, that allow for backward time travel in principle, but these require exotic conditions, such as rotating universes or negative energy densities, which may not be physically realizable. Most physicists believe that some version of the chronology protection conjecture, proposed by Stephen Hawking, prevents these scenarios from manifesting in reality. Still, the forward direction of time travel remains fully compatible with known physics. It blurs the line between science and philosophy, challenging our assumptions about identity, memory, and continuity. If two observers age at different rates due to space-time curvature or velocity, what does it mean to share a moment? What does it mean to be synchronized in a universe where time is not absolute? Time dilation also forces a reconsideration of causality. In a universe where time flows differently for different observers, the concept of simultaneity becomes relative. Events that are simultaneous for one observer may not be for another. This is not just a mathematical oddity, it reflects the fundamental structure of reality. Light cones, causal relationships, and the flow of time all depend on one's position and motion in spacetime. This relativity of simultaneity has profound implications for how we think about past, present, and future. There is no universal now, only sequences of events connected by light and causality. From this perspective, the universe is not a river of time carrying all things forward at the same rate. It is a complex topography of space and time, curved and tilted by mass and motion. Every object traces its own path through this terrain, and each path is governed by geometry. The passage of time is not dictated by a single clock, but by the world line of each traveler. Your heartbeat, your thoughts, your memories, all unfold along a curved thread of space-time that is unique to you. And so, while time appears linear in the rhythm of our days, the universe reveals it as a flexible dimension, shaped by context. Under general relativity, we are all travelers, not only through space, but through time, each of us moving forward along our own private axis of duration, influenced by where we are and how fast we move. It is a humbling thought that time itself, something we so often take for granted, is not an absolute. It bends, it stretches, it folds. The ticking of a clock on your wrist is not a universal truth. It is a local rhythm, a beat set by the gravitational curvature of your world and the motion of your journey. To live is to surf the contours of time itself, never quite in sync with anything else. And in that quiet divergence lies something beautiful, that no two beings, no two moments, no two paths through space-time are ever truly the same. Each of us experiences a slightly different universe, a slightly different flow, a slightly different now. And yet somehow we share it, curved, shifting, and deeply connected. Chapter 4. Free Fall and the Equivalence Principle. To understand gravity as Einstein saw it, one must begin not with stars or equations, but with falling. Not the kind of falling we fear or avoid, but a precise, universal kind, the kind that made Galileo drop spheres from a tower and Einstein imagine an elevator plummeting through space. Free fall, so ordinary on Earth, became for Einstein the key that unlocked a hidden truth about nature. In Newtonian physics, an object in free fall is one that has been released from rest and allowed to move under the influence of gravity alone. It accelerates downward because a force, gravity, acts on it, pulling it toward the center of the Earth. The force is proportional to the object's mass and inversely proportional to the square of the distance from Earth's center. That model works well for most of our everyday experiences. But something peculiar has always lurked in its simplicity. Different objects, regardless of their mass, fall at the same rate. A feather and a bowling ball, dropped in a vacuum, fall together. In Newton's equations, this occurs because the object's mass appears on both sides of the force equation and cancels out. But Newton never explained why that cancellation happens. It was simply accepted as fact. Einstein took that observation and gave it new meaning. He recognized that the equality of inertial mass, resistance to acceleration, and gravitational mass, response to gravity, is not just a mathematical coincidence, it's a profound clue. In his view, this equality suggested that gravity might not be a force in the traditional sense. Instead, what we interpret as a force might be something more subtle, something geometric. To explore this idea, Einstein considered the experience of an observer in a falling elevator. Imagine you're sealed inside a windowless elevator in deep space, far from any stars or planets. Suddenly, the elevator begins accelerating upward. You feel pressed to the floor. To you inside, it feels exactly like gravity. Now imagine a second elevator, one that is stationary above Earth, then cut loose so it begins to fall freely. Inside that falling elevator, you float. You no longer feel your weight. If you let go of an object, it hovers beside you. In that brief moment of descent, the elevator and everything inside it are all falling together under gravity's influence, making the force disappear from your perspective. Einstein saw these two experiences, accelerating in empty space and falling freely in a gravitational field, as fundamentally equivalent. This is the essence of the equivalence principle, the idea that local experiments in a small enclosed environment cannot distinguish between uniform acceleration and gravitational free fall. From this principle, he began to construct a new theory of gravity, not as a force, but as a property of spacetime itself. In this view, when you drop an object, it doesn't accelerate because a force pulls it down. Instead, it moves along a natural path, a geodesic, through curved spacetime. If the object is released and no other forces act on it, it will follow the straightest path allowed by the geometry of spacetime. The only reason you perceive it as falling is because you're not in free fall. You, standing on the Earth's surface, are actually being pushed upward by the ground, away from the geodesic your body would naturally follow. Gravity, in this formulation, is not pulling things down. Surfaces are pushing objects away from their natural trajectories. This perspective seems strange at first because it reverses how we think about motion. But it matches reality. Astronauts in orbit feel weightless, not because there's no gravity, but because they are in continuous free fall. Their spacecraft, their bodies, even the water droplets floating beside them, all follow the same curved paths through space-time. The sensation of weight disappears when you're no longer being prevented from falling. The equivalence principle has been tested with extraordinary precision. Physicists have dropped objects of different compositions in vacuum chambers, compared atomic clocks in free fall and at rest, and flown satellites with test masses isolated from other forces. Every time the results align, all objects fall identically, regardless of their properties, so long as only gravity acts. Even quantum tests using atomic interferometry confirm the principle at microscopic scales. These experiments reinforce Einstein's core insight. Gravity is not about forces acting on things. It's about the shape of the paths things take. This understanding allowed Einstein to generalize special relativity, which described the behavior of objects moving at constant speeds, into a broader theory that could also describe acceleration and gravity. In doing so, he extended the flat, inert geometry of special relativity into the dynamic, curved geometry of general relativity. Free fall became not just a state of motion, but the key to unlocking how space-time responds to energy and mass. When Einstein presented his full theory in 1915, it provided a new way of understanding gravitational phenomena that had puzzled scientists for decades. The strange precession of Mercury's orbit, which defied Newtonian predictions, emerged naturally from the geometry of curved space-time. Light bending around the sun, the slowing of time near massive bodies, the dynamics of black holes, all followed from this elegant principle that falling is indistinguishable from floating, and that acceleration and gravity are two sides of the same coin. What makes the equivalence principle so powerful is its local nature. It doesn't attempt to describe gravity everywhere at once, but focuses on what can be said in small regions of space-time, regions where curvature can be ignored or treated as uniform. In these local regions, the laws of physics take the same form as in special relativity. Light moves in straight lines, clocks tick at constant rates, and free-falling objects move uniformly. Only when comparing events at different locations, where curvature varies, do the effects of gravity emerge. In this sense, general relativity is a patchwork of locally flat regions sewn together by curvature. Even time, in this framework, becomes relative to the path an object takes through space-time. A clock in free fall does not tick more slowly because it is falling. It ticks at its proper time, measured along its geodesic. It is only when we compare that clock to one not in free fall that we see the difference. Gravity, therefore, is not acting directly on time. It shapes the path through which time flows. This insight also reshapes our understanding of what it means to be stationary. On Earth, we feel the force of gravity because we are being held up, resisted from falling by the ground beneath us. From the perspective of general relativity, we are accelerating upward relative to a freely falling frame. A satellite in orbit is actually the one experiencing no force. It is coasting along its natural geodesic. We, here on the surface, are the ones deviating from that natural motion. The counterintuitive nature of this truth can be unsettling. We are used to thinking of ourselves as stationary, held securely to Earth by gravity. But from space-time's point of view, it is the orbiting satellite that is free, and we who are under constant deviation from freedom. Gravity no longer pulls. Instead, geometry guides, and resisting that guidance produces the sensation of weight. The implications of the equivalence principle extend into other areas of physics as well. It has inspired attempts to unify general relativity with quantum mechanics by suggesting that gravity might emerge from more fundamental principles. Some approaches in theoretical physics, such as those involving entropic gravity or holographic duality, seek to explain space-time and gravity as emergent phenomena arising from information, thermodynamics, or entanglement. While none have yet succeeded in replacing general relativity, they all draw in part from Einstein's insight that the nature of gravity is deeply tied to how we experience motion and acceleration. At the heart of all of this is the simple realization that falling freely is indistinguishable from floating, that to let go is to return to the natural path determined by the universe's geometry, and that what we once thought of as force is instead a whisper in the structure of space and time. And so, every time you drop an object, every time it slips from your fingers and falls, you are witnessing not a pull, but a path. A quiet, ancient trajectory carved into the shape of the cosmos. The object is not being acted upon. It is being released. It is returning to the line it was always meant to follow. Perhaps that's all we're doing, that in the end, falling freely through a universe that bends around us, unaware of the deeper structure beneath our feet. And in that falling, we are not alone. We are part of a pattern, an unfolding, a geometry written long before we knew how to look. Chapter 5. Curved Paths in a Curved Universe. Motion through space has always carried with it an intuitive simplicity. From ancient observations of wandering stars to Newton's precise laws, humanity has long imagined that if left undisturbed, objects move in straight lines, and any deviation from that motion must result from an applied force. This idea formed the backbone of classical mechanics, where straight-line trajectories were the norm, and orbits were the result of constant acceleration caused by gravity. But Einstein's theory of general relativity replaces this mechanical picture with a geometric one. Objects do not move because they are pushed or pulled. They move because they are following the natural structure of spacetime. A planet orbiting a star, a comet tracing an elliptical path, or even a spacecraft drifting silently in the void, they all follow curved trajectories, not because something bends them, but because spacetime itself is curved, and they are simply tracing the straightest possible paths within it. In general relativity, the concept of a straight line is generalized to that of a geodesic. A geodesic is the path through spacetime that a free-falling object follows when no other forces are acting upon it. In flat spacetime, as described by special relativity, a geodesic is identical to a straight line. But in the presence of mass and energy, spacetime becomes curved, and the straightest path becomes a more complex trajectory, often appearing curved or even looping from an external point of view. This curvature is not a property of the object, but of the space through which it moves. Imagine placing a marble on a stretched rubber sheet. If the sheet is flat, the marble will roll in a straight line. But if you place a heavy ball on the sheet, it will deform, creating a dip. Now, if you roll the marble again, it will spiral toward the depression, curving as it follows the altered geometry of the surface. No external force acts laterally on the marble. It simply follows the shortest path available in the new geometry. This analogy, though imperfect, captures the essence of what general relativity proposes. Gravity is not a force, but a feature of the landscape. The presence of mass alters the shape of spacetime, and objects respond by following the contours of that shape. In the actual universe, this curvature occurs in 4 dimensions, 3 of space and 1 of time, and is described mathematically by the metric tensor, which specifies the geometry at each point. When mass or energy is introduced into this framework, the curvature changes, and the geodesics adapt accordingly. A star does not tug on a planet. It reshapes the spacetime around it, and the planet moves along the new geometry. The orbit of Mercury provides a concrete example of this phenomenon. For centuries, astronomers noted that Mercury's orbit shifted slightly with each revolution. While Newtonian mechanics could explain most of the motion, a small discrepancy remained. This anomaly was unaccounted for until Einstein applied his field equations to the problem. When he modeled the curvature of spacetime near the Sun and calculated Mercury's path as a geodesic in that curved geometry, the unexplained precession appeared naturally. It was one of the first major triumphs of general relativity and showed that the apparent deviation in Mercury's orbit was not due to unknown forces or unseen objects, but to the warping of spacetime itself. Curved spacetime also affects light. Although photons are massless, they still travel along geodesics, called null geodesics in this context. When a light beam passes near a massive object, its path bends, not because gravity is pulling on it, but because spacetime is curved in such a way that the straightest path itself is no longer straight in the Euclidean sense. This bending of light was famously confirmed during the 1919 solar eclipse, when starlight passing near the Sun was observed to shift position, validating Einstein's predictions and confirming that light, too, follows the geometry of the universe. But the implications go far beyond individual orbits or deflected beams. The geometry of spacetime determines the entire structure of cosmic motion. The rotation of galaxies, the behavior of galaxy clusters, and the evolution of the universe itself all arise from the curved pathways shaped by mass and energy. In this view, motion is no longer about objects pushing against one another, but about the universe guiding everything along invisible rails formed by geometry. On cosmological scales, general relativity reveals that spacetime itself is not only curved locally, near stars or black holes, but may be curved on the scale of the universe. Depending on the total amount of mass energy in the cosmos, the universe may be globally flat, positively curved like a sphere, or negatively curved like a saddle. These possibilities correspond to different global geometries, each with distinct implications for the shape, fate, and size of the cosmos. Observations of the cosmic microwave background suggest that the universe is very close to flat, meaning that on the largest scales, spacetime behaves like a Euclidean plane. But small curvatures remain possible, and in any case, local curvature dominates the experiences of objects like stars, planets, and us. Even in flat universes, local curvature due to galaxies and clusters remains deeply relevant. Gravitational lensing, one of the key observational tools in modern astrophysics, relies entirely on this principle. As light from distant galaxies passes through curved spacetime shaped by intervening mass, it bends and distorts, creating multiple images, arcs, or rings. These features are not artifacts of flawed optics, but natural outcomes of geodesics passing through dynamically curved geometries. One of the most counterintuitive ideas of general relativity is that stationary objects, such as a rock resting on the ground, are not following geodesics. In fact, they are being held in place by a force preventing them from following their natural path through curved spacetime. The ground pushes upward, deviating the object from free fall, and thus from its geodesic. Conversely, an object in orbit is actually moving along a geodesic. Though it may appear to be accelerating, it is in a state of pure inertial motion within a curved geometry. The curved path is not the result of a changing force, but the geometry defining what it means to move without force at all. Einstein's insight replaces the classical image of orbits as balances between centripetal and centrifugal forces with a cleaner, subtler concept. The orbit is simply what a straight path looks like when space and time are curved. The same is true of free fall. Objects fall not because they are drawn toward the Earth, but because their natural path through space-time dips inward toward the center of mass. The Earth's surface prevents us from continuing on that geodesic, which is why we feel weight. The apparent force we attribute to gravity is, in this sense, the result of resisting the natural geometry of our motion. The tools used to describe this geometry, tensors, connections, curvature scalars, may be mathematically abstract, but they encode physical reality. The Riemann curvature tensor, for instance, quantifies how space-time bends in the presence of energy. Through Einstein's field equations, this curvature is related directly to the distribution of matter and energy via the stress-energy tensor. In doing so, general relativity makes a profound statement. Motion arises from curvature, and curvature arises from content. The paths traced by planets, photons, and even empty space are all consequences of what resides within the universe. This geometric vision does not stop at astronomy. Even the passage of time itself, measured by clocks, is influenced by curvature. As established in earlier discussions, time passes differently depending on the geodesic an object follows and the curvature it experiences. The deepest implication of this is that every experience, every movement, every signal exchanged between particles is governed by geometry. The full power of general relativity becomes apparent when we consider how consistently it predicts physical behavior. Gravitational waves, observed a century after their prediction, are not mysterious emanations from deep space. They are ripples in the geometry of spacetime itself, propagating outward from cataclysmic events like merging black holes. These waves affect matter by stretching and compressing the distances between objects, not through traditional forces, but by altering the geometry through which they move. And yet, despite this complexity, the essential idea remains beautifully simple. Mass curves spacetime. Curved spacetime tells matter how to move. And that motion, from planetary orbits to cosmic expansion, arises not from mystical forces, but from geodesics through a flexible, responsive universe. In this framework, nothing is truly static. Even a lone object in the darkness of space is part of a broader structure, a curvature it both experiences and contributes to. The object's path, though it may seem empty or isolated, is guided by the geometry woven into the fabric of the cosmos. It is not alone. It is not disconnected. It is embedded always in a larger whole. And perhaps that is the most profound idea of all, that every motion, every orbit, every fall is not an act of separation, but a quiet unfolding of connection. The curve of your path is written by the stars. The shape of your time is guided by distant galaxies. In every movement, you are in dialogue with the universe itself. Chapter 6. Light bends and echoes through gravity. For much of human history, light was thought to be the fastest and straightest moving thing in the universe, an entity immune to influence, untouched by gravity or matter. In Newtonian physics, gravity affected only objects with mass, and light, having none, should have remained forever unbent, an untouchable probe of the cosmos. But general relativity, with its sweeping reimagining of gravity not as a force but as geometry, changed that understanding forever. In Einstein's framework, light does not travel through space as though the medium is flat and passive. Instead, light travels through spacetime itself, and when that spacetime is curved by mass or energy, the path of light must curve as well. The effect is not because gravity pulls on light in the traditional sense, but because the space-time that light moves through is itself bent. Light always moves along what are called null geodesics, the natural paths dictated by the curvature of space-time for entities that have no mass. These paths, when projected into space alone, often appear bent or distorted. This idea had a bold and testable prediction. If light from a distant star passed near a massive object, such as the sun, its path should curve, and the star would appear to shift position in the sky. In 1919, during a total solar eclipse, astronomers led by Sir Arthur Eddington confirmed this effect. Starlight that passed close to the sun was indeed deflected by an amount precisely predicted by Einstein's equations. It was the first observational triumph of general relativity, and the moment when the theory began to reshape not only physics, but the popular imagination. But the bending of light is not limited to stars seen during eclipses. It happens constantly throughout the universe, on scales large and small. Galaxies and galaxy clusters act as gravitational lenses, distorting and magnifying the light from more distant objects behind them. Sometimes this leads to visible effects like Einstein rings, perfect circles of light created when a background source, a foreground lens, and the observer are perfectly aligned. Other times, the result is more subtle. Multiple images of the same galaxy or quasar, arcs stretching across the sky, or faint duplications of light that has taken different curved paths to reach us. Gravitational lensing, as this phenomenon is known, has become one of the most powerful tools in astrophysics and cosmology. It allows us to study galaxies too faint or too distant to observe directly. It can reveal the presence of dark matter, an otherwise invisible form of matter, through its gravitational effects on light passing nearby. Because dark matter does not emit or absorb light, we cannot see it directly, but we can detect how it distorts the paths of light around it, mapping its distribution throughout the cosmos. Even more subtly, gravitational lensing can affect the cosmic microwave background, the afterglow of the Big Bang. As this ancient light travels across billions of years, it passes through the gravitational fields of intervening structures. These fields gently nudge the paths of the photons, altering the distribution of temperature and polarization we observe today. By studying these tiny distortions, cosmologists gain insight into the structure and evolution of the universe, as well as the nature of dark energy and the shape of space-time itself. Another profound consequence of curved space-time is the gravitational redshift of light. As light climbs out of a gravitational well, it loses energy, not in the sense of slowing down, since the speed of light remains constant, but by stretching its wavelength. This shift to longer, redder wavelengths is a prediction of general relativity and has been observed in laboratory settings and in astronomical environments. Light emitted from the surface of a white dwarf star, for instance, is redshifted due to the star's intense gravity. Similarly, light escaping from the edge of a black hole becomes so redshifted that, to an outside observer, it fades into invisibility, a phenomenon that defines the event horizon itself. Gravitational redshift is not just a curiosity, it has practical implications. The clocks aboard GPS satellites experience both special relativistic time dilation from their motion and general relativistic shifts due to the weaker gravity at orbital altitude. As a result, signals from the satellites are slightly redshifted compared to ground-based clocks. Engineers must correct for this shift to maintain the accuracy of positioning systems. Without accounting for the redshift, the entire GPS network would fail within hours. Another elegant prediction of general relativity is gravitational time delay, sometimes called the Shapiro delay. When light passes near a massive object, not only is its path bent, but the time it takes to traverse that path is increased. This delay arises because the geometry of space-time near mass is stretched compared to flat space. Even if the spatial distance between 2 points remains the same, the temporal interval increases. This effect has been measured with radar signals sent to planets and reflected back. When the signals pass near the Sun, they take slightly longer to return than expected, an effect that matches the predictions of general relativity with remarkable accuracy. Gravitational time delay has also been observed in more distant settings. When light from a quasar or supernova is gravitationally lensed by a galaxy, it can take multiple paths to reach us. Because each path traverses a different region of space-time, the light arrives at slightly different times. In some cases, we see the same cosmic event, such as a supernova, occur multiple times, each image appearing days, weeks, or even years apart. These echoes through gravity offer unique opportunities to measure the expansion of the universe, probe the structure of space-time, and test the predictions of general relativity under extreme conditions. Even gravitational waves, ripples in space-time caused by accelerating masses, interact with light in measurable ways. When a gravitational wave passes through a region, it stretches and compresses space-time itself. Light moving through that region is affected by these distortions. In detectors like LIGO, laser beams are split and sent down perpendicular arms. As a gravitational wave passes, the length of each arm changes slightly, causing the beams to shift in phase when they recombine. The result is a pattern that reveals the passage of the wave, not because the light itself is distorted, but because the space it travels through has changed. This interplay between light and space-time makes it possible to use photons as messengers, not just of the matter that emitted them, but of the geometry they've traversed. Every beam of light carries with it a memory of the space-time it moved through. Every deflection, every shift, every delay encodes information about the gravitational landscape it encountered. Light is not merely illumination. It is a probe, an explorer, and a silent archivist of the universe's shape. Perhaps one of the most dramatic applications of these ideas is in the study of black holes. Near a black hole, space-time is so curved that light can become trapped in orbit. There exists a region known as the photon sphere, where light can circle the black hole endlessly. If a photon enters this region at just the right angle, it can orbit indefinitely, though any slight deviation will either send it spiraling into the event horizon or escaping into space. These photon spheres contribute to the visual appearance of black holes and were crucial in generating the shadow observed in the Event Horizon Telescope's image of the supermassive black hole in M87. The light that grazes the photon sphere and escapes carries with it a distorted and amplified image of the surrounding space. Multiple images can be formed as light orbits the black hole several times before emerging, each image increasingly demagnified and delayed. These layers of light encode an intricate map of the black hole's geometry, a fingerprint of space-time under the most extreme conditions. Even in more modest settings, the interaction between light and gravity shapes how we perceive the cosmos. The expansion of the universe causes distant galaxies to appear redshifted, their light stretched as space itself expands. While this cosmological redshift is distinct from gravitational redshift, it is another way in which light reflects the nature of space-time. By measuring these redshifts, astronomers can determine how fast galaxies are moving away from us, and thus reconstruct the history and future of cosmic expansion. Together, these phenomena, bending, redshift, delay, and lensing, reveal a picture of light not as a passive traveler, but as a participant in the story of the universe. Light moves through space-time, but it also responds to it. The photons we detect in our telescopes are not just bearers of information from distant places. They are witnesses to curvature, to expansion, to distortion, and to delay. Every star we see, every galaxy we map, every flare we observe from the distant universe comes to us through a winding, curved, and gravitationally textured path. And yet, despite these twists and bends, light still arrives. Across billions of years and unfathomable distances, it travels with fidelity, bringing us echoes of ancient events, glimpses of unreachable places, and evidence of the very structure of space-time. It is light that allows us to see, but more profoundly, it is light that allows us to know. Perhaps then, the bending of light is not just a demonstration of gravity's reach, but a quiet reminder that in the deepest fabric of reality, even the straightest thing we know, the photon's path, yields to the shape of existence. And that in bending, light shows us how connected everything truly is. Chapter 7. Black holes, the ultimate curves in space-time. Among all the predictions of general relativity, few are as startling, extreme, or counterintuitive as the black hole. In the mathematical structure of Einstein's theory, black holes arise not as artificial constructs or theoretical indulgences, but as natural, unavoidable solutions to the field equations. They represent the ultimate expression of gravitational curvature, regions where space-time is no longer gently bent, but folded so severely that all paths lead inward, and nothing, not even light, can escape. The existence of black holes was first hinted at long before Einstein in the late 18th century, when scientists like Jean Michel and Pierre-Simon Laplace speculated that a sufficiently massive object could have an escape velocity greater than the speed of light. But without a theory of light as particles or a relativistic framework, these ideas remained little more than curiosities. It wasn't until Karl Schwarzschild in 1916 provided the first exact solution to Einstein's equations for a non-rotating, spherically symmetric mass that the black hole concept took a more rigorous shape. This solution revealed a critical radius, now called the Schwarzschild radius, within which the curvature of space-time becomes so intense that all geodesics, whether followed by particles or photons, converge inward. This boundary is known as the event horizon. It is not a surface in the traditional sense. It has no substance, no material structure. It is a one-way threshold. Once crossed, no signal, no information, and no influence can return to the outside universe. From the perspective of general relativity, the event horizon marks the boundary beyond which the known laws of physics cease to provide predictive power for external observers. What lies within the event horizon remains speculative, but according to classical general relativity, the collapse of matter continues inward, compressing into a single point of infinite density, a singularity. At this singularity, the curvature of spacetime becomes infinite, and tidal forces stretch and compress matter into oblivion. While such infinities are likely signs that general relativity breaks down at quantum scales, no complete theory of quantum gravity yet exists to replace this prediction. What is certain is that no known mechanism prevents collapse once the event horizon has formed, making black holes some of the most stable and persistent objects in the universe. Despite their terrifying mathematical properties, black holes are real astrophysical objects. They form naturally when massive stars reach the end of their nuclear life cycles. When a star runs out of fuel, it can no longer support itself against the inward pull of gravity. If the remnant core is sufficiently massive, no known force, not even the degeneracy pressure that holds white dwarfs and neutron stars apart, can halt the collapse. The result is a stellar mass black hole, typically several times the mass of our Sun, but occupying a region only a few kilometers wide. Such objects were once considered invisible, detectable only through indirect effects on nearby matter. But observational techniques have advanced dramatically. One key method is the study of accretion disks of gas and dust spiraling into a black hole. As material falls inward, it heats up due to friction and compression, emitting intense radiation, particularly in the X-ray spectrum. Space telescopes like Chandra and XMM Newton observe these emissions, allowing astronomers to detect black holes even when the event horizon itself cannot be seen. Another major breakthrough came with the observation of gravitational waves. When two black holes spiral toward one another and merge, they generate ripples in space-time, gravitational waves that travel outward at the speed of light. In 2015, the LIGO detectors made the first direct observation of such a signal, marking the dawn of gravitational wave astronomy. These waves carry information about the mass, spin, and distance of the colliding black holes, offering a new window into the dark and dynamic processes of the cosmos. Then, in 2019, came the first image of a black hole's shadow, captured by the Event Horizon Telescope, a global network of radio observatories working in synchrony. This composite image of the supermassive black hole at the center of galaxy M87 showed a dark central region surrounded by a glowing ring of light. The ring was not light emitted from within the black hole, but rather from hot gas swirling just outside the event horizon, bent and focused by the intense gravitational lensing. The image confirmed predictions made decades earlier, including the size and shape of the shadow cast by the event horizon on the glowing backdrop of inflowing matter. Black holes vary in size from the stellar mass kind formed in supernovae to the supermassive ones found at the centers of galaxies, which can contain millions or even billions of solar masses. The origin of these supermassive black holes remains an open question in astrophysics. They may have formed from the collapse of massive primordial clouds or through the mergers of many smaller black holes and stars over cosmic time. Whatever their origin, they play a crucial role in galactic evolution, regulating star formation through feedback mechanisms powered by accretion and relativistic jets. Some galaxies contain active galactic nuclei, where matter falling into a supermassive black hole releases enormous amounts of energy, outshining the combined light of billions of stars. These objects, known as quasars when viewed from afar, are powered by the conversion of gravitational potential energy into radiation. Infalling matter heats to extreme temperatures, emitting light across the electromagnetic spectrum. These phenomena provide not only a laboratory for testing extreme physics, but also a means of probing the early universe, since many quasars are seen at great distances, revealing conditions billions of years ago. The physics near black holes also challenges our understanding of information and entropy. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now known as Hawking radiation. This radiation is incredibly faint for astrophysical black holes, but has profound implications. It suggests that black holes can slowly lose mass and eventually evaporate over timescales far longer than the current age of the universe. This leads to the so-called black hole information paradox. If Hawking radiation is purely thermal and carries no information about the matter that fell in, then information appears to be lost when a black hole evaporates. This contradicts a core principle of quantum mechanics, that information must be conserved. Resolving this paradox is a major challenge in theoretical physics, and several proposed solutions, ranging from holographic principles to quantum entanglement across the horizon, are currently under investigation. Black holes also raise profound questions about the nature of spacetime itself. Near the event horizon, coordinate systems behave strangely. Time for an outside observer appears to slow to a halt as an object approaches the horizon, while the falling object experiences no such slowdown. This discrepancy is not an illusion, but a real consequence of the geometry of spacetime. The division between what is visible and what is not, between causally connected and disconnected regions of the universe, becomes sharp and absolute. In theoretical extensions of general relativity, even more exotic objects are predicted. Solutions such as the Kerr metric describe rotating black holes which possess not just mass but angular momentum. These rotating black holes exhibit complex structures, including ergospheres, regions outside the event horizon where no object can remain stationary, and the possibility of extracting energy through processes like the Penrose mechanism. Some solutions even allow for hypothetical wormholes, tunnels through spacetime that might connect distant regions, but these require forms of matter or energy that violate known physical laws. Despite these speculative extensions, the core concept remains solid. Black holes are not science fiction. They are testable, observable, and deeply integrated into our understanding of the universe. They serve as the ultimate laboratories for physics, where theories are pushed to their limits and where new physics may one day be discovered. Their formation, evolution, and interactions shape galaxies, seed quasars, and emit gravitational waves that ripple across the universe. They also serve as boundaries, both literal and conceptual. Boundaries beyond which we cannot see, cannot send signals, cannot retrieve data. And yet, these boundaries are not just limits. They are portals to deeper understanding, to more refined theories, to questions still unanswered. They remind us that even the most elegant theories may reach an edge, and that at those edges, new insights await. Perhaps what makes black holes so compelling is not just their power or their mystery, but their precision. They are not chaotic or arbitrary. They obey the laws of physics with an exactness that challenges us to refine those laws further. They are the ultimate expression of curvature, the final answer to what happens when gravity is taken to its logical extreme. And yet, in their silence, in their darkness, they speak volumes. They tell us that nature does not flinch from extremes, that the fabric of reality can stretch, fold, and collapse in on itself, and that even in those places where no light escapes, something fundamental is preserved. The unity between geometry and motion, between energy and space, between time and its end. Chapter 8. Gravitational waves, ripples in the fabric of reality. In the framework of general relativity, mass and energy shape the geometry of spacetime, and in turn, that geometry dictates how matter and light move. For many years after Einstein's theory was published, physicists understood that this interaction could be static, like the persistent curvature around a star or a planet. But the equations also implied something more dynamic. If space-time could bend, then it could also ripple. And if those ripples could propagate outward, then gravity, like light, might carry energy across the cosmos in the form of waves. These hypothetical distortions are known as gravitational waves. They are not vibrations in a medium like air or water. They are not waves traveling through space. They are waves of space, oscillations in the very metric that defines distance and time. As they pass through a region, they stretch and compress space-time itself, altering the relative positions of objects without applying any force in the traditional sense. These waves are fantastically weak, difficult to detect, and yet they are among the purest messengers the universe can offer. Unlike light or particles, they are unaffected by dust, gas, or magnetic fields. They pass through matter with near impunity, preserving the imprint of the cataclysmic events that produced them. Einstein first predicted the existence of gravitational waves in 1916, just 1 year after completing his general theory of relativity. The mathematical foundation was clear, but whether these waves could be physically real and whether they could ever be observed remained topics of debate for decades. Some believed they might be mere artifacts of coordinate choice, mathematical ripples with no measurable consequences. Others argued they must exist, but would be so weak that no instrument could ever detect them. The generation of gravitational waves requires the acceleration of mass, but not just any motion will do. Because gravity is a quadruple interaction, meaning it cannot radiate energy from spherically symmetric motion, objects must accelerate asymmetrically. A pair of orbiting stars, for example, constantly changes the shape of the gravitational field around them, sending out ripples in the geometry of space-time. The more massive the objects and the faster they move, the stronger the signal. The most powerful gravitational waves come from the most violent processes in the universe: black hole mergers, neutron-star collisions, and core collapse supernovae. For many years, the evidence for gravitational waves was indirect. In 1974, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system, two neutron stars orbiting each other with extraordinary precision. Over time, they observed that the orbit was shrinking, with the two stars spiraling slowly toward one another. The rate of this orbital decay matched perfectly the predictions of general relativity, assuming that gravitational waves were being emitted and carrying energy away. This discovery earned them the Nobel Prize in Physics and provided the first compelling observational support for gravitational wave theory. But the waves themselves still had not been directly detected. That changed in 2015, nearly a century after Einstein's prediction, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made history. On September 14th of that year, detectors in Livingston, Louisiana and Hanford, Washington recorded the passing of a gravitational wave. The signal matched the theoretical waveform of two black holes, each about 30 times the mass of the Sun, merging over 1 billion light-years away. In just a fraction of a second, the black holes coalesced, releasing a burst of gravitational radiation that briefly exceeded the total power output of the observable universe. But by the time the wave reached Earth, its effect was tiny, changing the length of LIGO's 4-kilometer arms by less than 1,000th the diameter of a proton. LIGO works by using laser interferometry. A beam of laser light is split and sent down two perpendicular arms. The light reflects off mirrors and returns to the starting point, where the beams are recombined. If a gravitational wave passes through, it slightly stretches one arm while compressing the other, creating a telltale interference pattern in the recombined light. The engineering precision required to isolate such minuscule distortions is staggering. Vibrations from seismic activity, traffic, or even thermal fluctuations in the atoms of the mirrors must be meticulously filtered out. But when the signal emerges, clean, distinct, and matched to theoretical models, it carries with it the fingerprint of a distant cosmic dance. Since that first detection, dozens more gravitational wave events have been observed, including mergers between black holes, collisions between neutron stars, and mixed systems of black holes and neutron stars. These discoveries have expanded our understanding of stellar evolution, compact objects, and the population of massive remnants in the universe. In 2017, the detection of a neutron star merger, GW170817, was observed not only in gravitational waves, but across the electromagnetic spectrum. Telescopes around the world captured the fading light from the aftermath of the collision, revealing the creation of heavy elements like gold and platinum. This event marked the beginning of multi-messenger astronomy, where gravitational waves and light combine to provide a richer view of the universe. Gravitational waves have also opened new avenues for testing general relativity. By analyzing the detailed structure of the waveforms, how quickly they rise and fall, how they shift in frequency, scientists can test the predictions of Einstein's equations in the strongest gravitational fields ever observed. So far, the results have been remarkably consistent with general relativity. No deviations have been found, no signs of alternative theories emerging. But the search continues, and as detectors become more sensitive, they may uncover subtle differences or new phenomena that hint at deeper physics. Current observatories like LIGO and Virgo are already being upgraded, and new detectors such as CAGRA in Japan and the planned Einstein telescope in Europe will increase both sensitivity and coverage. Perhaps even more transformative will be LISA, the Laser Interferometer Space Antenna, a European Space Agency mission scheduled for the 2030s. LISA will consist of 3 spacecraft orbiting the Sun in a triangle millions of kilometers apart, detecting gravitational waves with periods far longer than ground-based instruments can measure. This will allow it to detect signals from supermassive black hole mergers, extreme mass ratio inspirals, and possibly even waves from the early universe. At the largest scales, some scientists hope to detect a gravitational wave background, a persistent hum of waves from countless unresolved sources, or even from primordial events shortly after the Big Bang. This background, if discovered, would serve as a cosmic fossil, preserving information about epochs otherwise inaccessible to direct observation. Pulsar timing arrays, networks of precisely monitored pulsars, are already seeking this signal by looking for correlated fluctuations in the arrival times of pulses due to passing gravitational waves. Preliminary hints have emerged, suggesting that the background may be within reach. What makes gravitational waves so remarkable is that they extend our senses. For centuries, astronomy was limited to what we could see, and later to what we could detect across different forms of light. Gravitational wave astronomy is not a replacement for electromagnetic observation. It is a new sense entirely. It reveals objects invisible to telescopes, events hidden behind gas and dust, and motions too subtle to emit light. It is like hearing the universe for the first time, not in metaphor, but in physical truth. The signals we now detect were always there, always passing through us. We just didn't know how to listen. Each detection is a record of movement, a fossil of motion in spacetime. Where light tells us what something looks like, gravitational waves tell us how something changed. They do not scatter. They do not reflect. They carry the story directly, unedited, across billions of light years. A black hole merger that took place before life arose on Earth can shake our detectors today, connecting our present to a past far beyond memory. In the coming decades, gravitational waves may also help answer some of the deepest questions in physics. They may provide clues about the behavior of matter at nuclear densities, the limits of neutron star stability, or the equation of state for ultra-dense matter. They may hint at the nature of dark matter if compact objects made of exotic material contribute to the observed signals. And they may one day point toward a unification of general relativity with quantum mechanics, revealing cracks in the smooth fabric of classical gravity. The ripples that travel through space-time are not loud. They do not announce themselves with brilliance or color. They pass quietly, gently stretching the dimensions of space and time as they go. And yet, in those subtle distortions lies an entire narrative. The slow collapse of orbiting stars, the final breath of a massive core, the echo of symmetry broken in the early cosmos. Gravitational waves are silent messengers, but they carry deep truth. And perhaps that is what makes them feel so profound. That the universe does not speak only in light. That sometimes the cosmos whispers, and if we listen carefully enough, we can feel it moving. Chapter 9. Testing Einstein, How We Know It's True. A theory is only as powerful as its predictions, and only as trustworthy as the experiments that verify them. When Albert Einstein published his theory of general relativity in 1915, he offered not just a reinterpretation of gravity, but a radical reshaping of our understanding of space, time, and the geometry of the universe. Yet elegant mathematics and philosophical appeal alone are not enough to validate a scientific theory. General relativity made specific, testable predictions about the behavior of light, the motion of planets, the ticking of clocks, and the transmission of gravitational influences. Over the following century, those predictions have been tested in one of the most rigorous and expansive programs of empirical scrutiny in the history of science. Perhaps the earliest and most iconic test came in 1919. Einstein had predicted that light would bend as it passed near a massive object like the sun, not because the sun exerted a force on photons, but because its mass curved the space-time through which the light traveled. During a total solar eclipse that year, teams of astronomers led by Arthur Eddington photographed stars whose light passed close to the sun's edge. When the sun's brilliance was momentarily blocked, they could see that the stars appeared displaced, shifted slightly outward from their expected positions. The amount of bending matched Einstein's prediction, and the result catapulted general relativity from mathematical speculation into the realm of observable reality. But that was only the beginning. One of the strongest early confirmations came from the motion of Mercury, the innermost planet in the solar system. For centuries, astronomers had puzzled over the slow rotation of Mercury's orbit. Its perihelion, the point of closest approach to the Sun, shifted slightly with each revolution. Newtonian mechanics could account for most of the precession due to perturbations from other planets, but not all of it. About 43 arcseconds per century remained unexplained. When Einstein applied his equations to the curvature of spacetime near the Sun, the discrepancy vanished. General relativity provided precisely the amount of additional precession needed. This success offered not just a checkmark, but a quantitative triumph, turning a long-standing anomaly into a signature prediction. Another crucial area of confirmation involves time itself. One of general relativity's boldest implications is that time does not pass uniformly across space. In regions of stronger gravity, time moves more slowly compared to regions of weaker gravity. This gravitational time dilation was tested directly in 1960 using an experiment known as the Pound-Rebka test. Gamma rays were emitted from the top of a tower and detected at the bottom, where Earth's gravity was slightly stronger. The frequency of the gamma rays shifted in exactly the manner predicted by Einstein's equations, confirming that time had indeed flowed differently over the short vertical distance. Later experiments extended this to ever greater precision. Atomic clocks flown in airplanes or carried to mountain peaks ticked at slightly different rates than identical clocks at sea level. Satellite-based systems, such as the Global Positioning System, must account for both special and general relativistic effects to maintain accuracy. The onboard clocks and GPS satellites tick faster due to the reduced gravitational potential in orbit. If engineers ignored these relativistic effects, even though they amount to mere nanoseconds per second, location errors would accumulate rapidly, leading to positional drift of kilometers each day. The practical necessity of relativistic corrections provides one of the most everyday demonstrations of the theory's predictive power. Beyond Earth, the behavior of binary pulsars, rotating neutron stars locked in close orbits, has offered profound confirmation of general relativity in strong gravitational fields. The Hulse-Taylor pulsar system, discovered in 1974, allowed astronomers to measure the orbital decay caused by the emission of gravitational radiation. The rate of orbital tightening matched exactly the predictions from general relativity, providing indirect but compelling evidence for gravitational waves long before their direct detection. Over time, additional binary pulsars have been found and studied, and each system has reinforced the theory's accuracy. In the realm of light propagation, gravitational lensing, the bending and distortion of light by massive objects, has become both a tool and a test. Astronomers routinely observe galaxies whose light has been curved around other galaxies or clusters, forming arcs, rings, or multiple images. These observations match detailed simulations based on Einstein's equations. Moreover, when background sources vary in brightness over time, such as quasars, the lensed images vary with slight time delays. These delays encode the curvature of spacetime along different paths and have been used to test the theory on cosmological scales. One of the most striking demonstrations came with the Event Horizon Telescope in 2019. By linking radio observatories across the globe, astronomers created a virtual Earth-sized telescope capable of resolving the region near a black hole's event horizon. The image of the supermassive black hole in galaxy M87 revealed a bright, asymmetric ring of light encircling a dark shadow, consistent with predictions made decades earlier. The size and shape of the shadow, as well as the lensing of light around it, matched models derived from general relativity, confirming the theory's applicability in extreme conditions near a black hole. The arrival of gravitational wave astronomy has brought even more precise and dynamic tests. When LIGO first detected a gravitational wave in 2015, the waveform was not merely an unexpected signal. It was a fingerprint of two black holes spiraling into each other and merging. The shape of the wave, its frequency, and its amplitude evolution all matched numerical simulations derived from Einstein's field equations. Since then, dozens of events have been recorded, each one allowing scientists to probe the theory in new ways. Observations of neutron star mergers, in particular, have allowed researchers to test general relativity not only through gravitational waves, but also through light, as the collisions emit gamma rays, visible light, and other electromagnetic signals. No deviations have been found. Across scales, from subatomic timing to cosmological motion, general relativity has passed every test. But physicists do not take this success as final proof. They seek areas where the theory might break down, both to refine their understanding and to find hints of deeper physics. For instance, the theory does not yet account for the quantum nature of particles and fields. In regions of extreme curvature, such as the center of black holes or the origin of the universe, quantum gravitational effects are expected to become important. Yet general relativity is a classical theory with no inherent quantum structure. Bridging that gap is one of the grand challenges of modern theoretical physics. In some scenarios, proposed alternatives to general relativity introduce new fields or modify the equations slightly to explain phenomena like cosmic acceleration or the nature of dark energy. These alternatives often reduce to Einstein's theory in familiar situations, but diverge under extreme conditions. Testing these differences requires ultra-precise observations. Ongoing and future missions, such as the LISA Gravitational Wave Observatory, the Euclid Space Telescope, and pulsar timing arrays, aim to explore regimes where new physics might reveal itself. Even the constancy of the speed of gravity has been tested. When gravitational waves and light from the neutron star merger GW-7817 arrived nearly simultaneously, despite traveling over 100 million light-years, scientists confirmed that gravitational waves move at the speed of light to within a fraction of a percent. This ruled out entire families of modified gravity theories and reaffirmed Einstein's original formulation. The breadth of experimental confirmation for general relativity is vast. From solar system tests to binary stars, from GPS corrections to black hole images, from gamma-ray shifts to space-time ripples, the evidence forms a coherent, interlocking web. It is one thing to make a single correct prediction. It is another to predict, with unwavering accuracy, the outcome of hundreds of tests across nearly every branch of physics and astronomy. Still, the very strength of general relativity invites scrutiny. The more successful a theory, the more important it becomes to probe its limits. Physicists continue to test for violations of the equivalence principle, the constancy of physical constants, and possible quantum deviations in gravitational behavior. The search is not driven by doubt, but by curiosity. If the theory does break down somewhere, that crack may be the doorway to the next stage in our understanding of reality. What makes Einstein's work endure is not just that it has passed so many tests, but that it invited so many in the first place. It provided a framework not merely to explain existing data, but to anticipate phenomena we had never before imagined. It guided the design of satellites, observatories, and missions decades before the necessary technology existed. And when the instruments finally caught up, the universe behaved exactly as the equations had predicted. There's something quietly profound in that consistency, that the patterns traced in chalk on a blackboard a century ago now describe the behavior of galaxies, the ticking of satellite clocks, the bending of light, and the shudder of space-time itself. That a mind on Earth once peered into the nature of geometry and found the universe written there. And perhaps that is the real test of Einstein's theory, not only that it is true, but that it makes reality itself more intelligible. In the curves of space-time and the rhythm of falling objects, we glimpse not just accuracy, but clarity, a harmony between thought and world. Chapter 10. The Edges of Understanding, where relativity meets quantum physics. General relativity and quantum mechanics are the two great pillars of modern physics. Each is a triumph of human understanding, elegant, predictive, and experimentally verified to astonishing precision. General relativity describes the world of the very large, the motion of planets, the bending of starlight, the warping of space-time around black holes, and the expansion of the universe itself. Quantum mechanics, in contrast, rules the realm of the very small, electrons and atoms, photons of light, the behavior of subatomic particles, and the fundamental uncertainties built into nature. Each theory works extraordinarily well in its own domain, but they are not compatible with one another. At ordinary scales, this incompatibility is unnoticeable. For most practical purposes, the effects of both theories can be applied independently. A GPS satellite uses quantum mechanics to operate its atomic clock and general relativity to correct for gravitational time dilation. Each part of the system works because it applies to different aspects of the satellite's operation. But in extreme environments, where very strong gravitational fields interact with very small distances, this separation breaks down. In these domains, such as the center of a black hole or the first moments of the Big Bang, both theories must apply simultaneously. And when they are brought together, contradictions emerge. General relativity treats space-time as continuous and smooth. It is a geometric object whose curvature changes in response to mass and energy. The Einstein field equations describe how this curvature evolves, and the solutions are deterministic. Given initial conditions, the theory predicts what spacetime will look like at all future times. It is a classical theory in the deepest sense. Quantum mechanics, by contrast, is probabilistic. It introduces a fundamental uncertainty into nature, embodied in Heisenberg's uncertainty principle. Particles do not follow precise paths. Instead, they exist as wave functions, clouds of probability describing where they might be. Quantum theory also introduces discrete quantities, energy levels, spin states, and the quantization of fields. It is a world built from indivisible units and governed by inherent fuzziness. Bringing these views together, quantizing a geometric fabric, proves immensely difficult. Efforts to merge them have produced various lines of inquiry, none of which is yet complete. One of the earliest approaches was quantum field theory in curved spacetime, which treats matter and radiation as quantum fields but keeps gravity classical. This semi-classical approximation has had success in limited domains, such as explaining Hawking radiation, the theoretical prediction that black holes emit thermal radiation due to quantum effects near the event horizon. But it is not a full quantum theory of gravity, because it treats spacetime as a passive stage rather than a dynamic quantum entity. A complete quantum theory of gravity would treat spacetime itself as quantized. That is, just as matter is made of atoms and energy is made of photons, space and time would be composed of discrete units, perhaps tiny loops, strings, or spin networks. Several theoretical frameworks attempt to describe this possibility. String theory is one such candidate. It proposes that the fundamental constituents of the universe are not point particles, but one-dimensional strings vibrating at different frequencies. These strings naturally include a graviton, a hypothetical quantum particle that mediates gravity, suggesting that gravity might emerge from string dynamics. String theory also predicts extra dimensions beyond the familiar four, compactified on scales too small to observe directly. In this higher dimensional framework, the apparent conflict between relativity and quantum mechanics might be resolved by embedding both in a more fundamental theory. Another approach is loop quantum gravity, which attempts to quantize spacetime directly without requiring extra dimensions. In this model, spacetime is represented as a network of finite loops of quantum geometry. These loops form a spin network, and the evolution of this network over time describes a spin foam. Loop quantum gravity predicts that space and time are discrete at the Planck scale, around 10 nomius spin meters. In this picture, smooth spacetime emerges as an approximation, much like fluid behavior emerges from molecules. Despite their differences, both string theory and loop quantum gravity attempt to do the same thing. Describe a quantum version of gravity that reduces to general relativity on large scales and agrees with quantum mechanics on small ones. Yet neither has been experimentally confirmed. One reason is that the effects of quantum gravity are expected to be extremely subtle, only significant near singularities or in the early universe. Testing these ideas directly requires energy scales far beyond those currently accessible by particle accelerators. Still, indirect tests may eventually come. Some theorists propose that quantum gravitational effects could leave traces in the cosmic microwave background, the afterglow of the Big Bang, or in high-energy astrophysical phenomena like gamma-ray bursts. Others hope that tiny violations of known symmetries, such as Lorentz invariants, might offer clues. Even gravitational waves already detected from black hole mergers could someday carry imprints of quantum corrections if our detectors become sensitive enough. Another area of tension lies in the information paradox. According to quantum mechanics, information about a physical system is never lost. It may be scrambled, but it remains preserved. Yet if black holes evaporate through Hawking radiation, and that radiation is purely thermal, then information about the matter that fell into the black hole appears to be destroyed. This conflicts with the principle of unitarity in quantum mechanics. Resolving this paradox remains one of the key unsolved problems in physics. Some propose that information escapes in the radiation after all, in ways not yet understood. Others suggest that black holes may store information on their event horizons, a possibility captured in the holographic principle. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional information on a two-dimensional surface. This idea emerged from studies of black hole entropy, particularly the work of Jacob Bekenstein and Stephen Hawking, and has been developed further in the context of string theory and the ADS-CFT correspondence. These concepts hint at a radical possibility that spacetime itself might be emergent, arising from more fundamental quantum processes. If that is true, then general relativity would not be a fundamental theory, but an effective one, an approximation that emerges from a deeper quantum reality, just as thermodynamics arises from the collective motion of molecules. In this view, gravity, space, and time are not primary ingredients of the universe, but emergent phenomena arising from quantum entanglement, information theory, or other foundational structures. This line of thought also suggests that time itself might not be fundamental. In quantum mechanics, time is usually treated as an external parameter, not an operator like position or momentum. But if space-time is quantized or emergent, then time may arise from correlations between quantum systems, a statistical property rather than an absolute dimension. Such ideas challenge our deepest assumptions and open the door to a radically new understanding of causality, chronology, and the structure of the universe. Despite the elegance and ambition of these theories, the path forward remains uncertain. There is no consensus on which approach, if any, will ultimately succeed, nor is it clear what kinds of experiments might decisively verify a quantum theory of gravity. Some physicists are exploring analog systems, laboratory experiments that simulate aspects of black holes or expanding universes. Others are focused on finding mathematical consistency, believing that a coherent and beautiful theory must eventually connect to reality. The tension between general relativity and quantum mechanics is not a sign of failure, but a signal of incompleteness. Both theories have passed every test in their respective domains. Yet nature, in its fullness, encompasses both gravity and quantum behavior. Somewhere in the deep structure of space-time and matter, the two must come together. The search for this union is not merely a technical pursuit, it is a philosophical one, touching on the nature of existence, the meaning of measurement, and the ultimate architecture of reality. For now, we live in a world where both theories are true, but not yet unified, where black holes bend space-time while entangled particles defy classical intuition, where the expansion of the universe and the jitter of electrons coexist in uneasy silence. And in that silence, the next great theory waits. Something beyond geometry and probability, beyond curvature and collapse. Perhaps one day, we will look back at both general relativity and quantum mechanics as stepping stones, brilliant but partial, on the way to a deeper insight. A theory that will not only describe the edge of black holes and the birth of the cosmos, but will also explain why space, time, and existence themselves came to be. And until then, we listen to the curve of gravity, to the whisper of particles, to the faint echo at the boundary between the known and the unknowable. And now, my friend, if your eyes are still open and your mind still curious, there's another journey waiting for you, just one click away. But if sleep has already wrapped you in its quiet embrace, then may your dreams carry you gently through the stars. Until next time, rest well and remember, the universe is always here, quietly unfolding around you.